guys, in previous video we have talked about radius of curvature in Cartesian coordinates. So in this video, radius of curvature in polar coordinates. I will give first video link in description. So let's get started. Radius of curvature in polar coordinates. So you know what is radius of curvature, which is covered in last video, the first part. So the formula for radius of curvature in polar coordinates is this. This is an important formula which we are going to use throughout this class, this session. So please just give a 2 seconds to just remember this formula. Rho is equal to r square plus r1 square whole to the power 3 by 2 divided by r square plus 2r1 square minus r2. So what is r is nothing but the given equation in polar form. So this is given in the question, r, and r1 is nothing but the first derivative with respect to theta. This is very important. And r2 is nothing but double differentiation with respect to theta again. So this is the first example. So find the radius of curvature of a cardioid. This is a given equation r, and show that rho square by r is a constant. So there are two questions in this single question embedded into a single question. So if you see carefully, first we have to find the radius of curvature and we have to show that r square by r is a constant. So just find out. First step, we have to differentiate it. So this is formula which we are going to use here. So remember this is very important formula. And now just differentiating, first differentiate with respect to theta. So just differentiate, you get minus a sin theta, and again differentiate with respect to theta, you get minus a cos theta. So now r square plus r1 square, we are finding out this. Why? Because this is nothing but your numerator term inside this. So just finding out r square plus a square sin square theta. So r is nothing but the given equation which you know, which is a into 1 plus cos theta. So just substitute here and just simple multiplication, you get 2ar, and just raising it to the power 2ar to the power 3 by 2 because it's in formula. So just we are getting it up, and now we are coming to the denominator. So just simplifying the denominator by substituting the things which are present there. So now simply r square, r you know that which is the given equations, and simply multiply blah blah blah, you used to get a 3ar. Now we are putting everything in the formula which is there present. So we are putting up everything in this formula, used to get radius of curvature. And now this is the radius of curvature. Now we are squaring it up. Why we are squaring it up? Because to show that this is a constant. So rho square by r, so just square it up divided by r, you get the constant term, so which is constant, hence proved. So now second question, find the radius of curvature at any point on a curve r to the power n is equal to a to the power n sine n theta, where a is a constant. So now first, if you got this type of question, first of all just wait, because you should not differentiate straight away, because if you differentiate it, it goes on. So it will be difficult, because if you differentiate this kind of things, the things will get added up and the big equation you used to get it. So that's not recommended. First, if you get it, just apply log on both sides to get a simpler equation. So if you apply log on both sides, these n will come down, because that's that's about log anything to the power n will comes down. So just we get this equation. So this is very easy to differentiate, and now differentiate it with respect to theta. So now we differentiate it log 1 by r dr by d theta, and now keeping dr by d theta, you have to get it, and this is nothing but a constant, so it will be as 0 if you differentiate it. And log of sine and theta, log of n sine theta is nothing but 1 by sine and theta cos and theta, because it's a chain rule. By using chain rule we used to get this, and r1 we got it. Right now r2 nothing but you take this is a u and this is a v. Just see they are applying uv formula here to differentiate it in another time. So apply uv formula, you used to get r2. Now as it is r square plus r1 square, just finding out and raising it to the power 3 by 2, you get this. And now the denominator term, just a simplification, you used to get this, and now putting it in the formula, which is nothing but this formula, used to get the radius of curvature. That's it. So if you see here, sine and theta is replaced into a to the power n by r to the power n. Why do you know? That's nothing but the given equation. So see, the given equation is r to the power n, a to the power n, sine to the power n, sine and theta. So sine and theta is nothing but rn by an. So that's it done here. So now we are going to another concept, which is radius of curvature at origin. So sometimes it may be easy. In a straightaway method, you can find it out. In a previous method, you can find it out at origin and keeping as a point 0, 0. But sometimes it may not come as easy questions. So at that time, you have to follow this type of approach to solve that kind of questions. So if curve y is equal to f of x passes through the origin, the x-axis is a tangent at origin. This is very important. So there is a curve which passes through origin. For that curve, x-axis is acting as a tangent. So in origin, then the radius of curvature is given by this formula. When this formula we have to use, very important, because in x-axis is tangent. If x-axis act as a tangent, then we have to use this formula. Rho is equal to limit x tends to 0 x square by 2y. If x-axis is a tangent, then x square by 2y. You have to remember this. So this is a proof which we don't need. And next one, same. If y is equal to f of x passes through the origin, if y-axis is a tangent, here there's a different. There is an x-axis, here is a y-axis. Y-axis acting as a tangent at origin, then rho is given by y square by 2x. This is x square by 2y. This is y square by 2x. Be very careful in this. So this is again a proof which we don't need. And now a third case is there. So if there is a curve which passes through origin 0, 0, but neither the x-axis nor the y-axis is tangent for the origin, then we have to use this formula. So while looking up this formula, you may get it out. What is P and Q? Which we never seen before. So P and Q is nothing but P is equal to f dash of 0. Differentiate it respect to if this differentiate it first time, and so it is y. No, so just differentiate it with respect to x, so dy by dx. So differentiate it and put 0 in the place of x. And similarly, second derivative, p is first derivative, so p is f dash of 0, q is f double dash of 0. So for this little bit proof is important, no, like unlike other, for this proof is somewhat important because we need this equation which is present in the proof. So y is equal to f of x is equal to f of 0 plus x by 1 factorial f dash of 0 plus x square by 2 factorial f double dash of 0. So it goes on. So you just remember this formula which we are going to use in the in the upcoming problems. So from this, p is nothing but f dash of 0, q is nothing but f double dash of 0. So just replace it with p and q. It looks like this. So now at the origin, this is the radius of curvature for a curve passing through origin, but neither x-axis nor the y-axis tangent. So here is an important point. In a curve passes, so this is nothing but a procedure. The given curve passes through the origin, then the equation of a tangent at the origin is obtained by equating the lowest degree term to 0, which we are going to see in this problem, this example problem. So what's the problem? Find the radius of curvature at origin for x cube y cube to x square 6xy is equal to 0. So now we are going to find the radius of curvature at origin for this curve. So if you see here, what is the lowest degree term? This is third degree, so it's power 3. It's also third degree, it's second degree, but this is a single degree. So we are going to find we are going to equate this lowest degree term to 0. If you 6y, yeah, sorry, 6y is equal to 0, then 6 goes there, so it's nothing but y is equal to 0. Y is equal to 0, the equation of x-axis. What is the equation of x-axis? That's nothing but the y is equal to 0. So what do you get from this? This is nothing but the tangent. So y is equal to 0 represent that x-axis is the tangent at origin at that curve, for the curve. So now we know that for x-axis as a tangent, this is a formula x square by 2, limit x tends to 0, x square by 2y. So now if you see the equation, there is none of the term like this, x square by 2y. Nothing is there. So we have to make it. So just to make it, we have to divide the equation by y. So just divide the given equation by y, you used to get this. And here there are present x square by y. So here take out on x. So it's done here. So now it's at origin, so x should be 0, y should be 0. So now put x is equal to 0, y is equal to 0, but you have to put this as a radius of curvature rho. So see, it's substituted here, 2 rho, it's 2 rho. Why 2 rho? Because this 2 we are bring it to the left side, so it's happened here. So that's why 2 row. And now put x is equal to 0, y is equal to 0, you have to get rho is equal to 3 by 2. That's nothing but that our intent. That's the radius of curvature of the curve at origin. So find the radius of curvature at origin for this. So again we have to do the similar things. Equate the lowest degree term to 0. If you lowest degree terms x is equal to 0, if you equate 2x is equal to 0, then x is equal to 0. That implies that y-axis is a tangent at that origin. So similarly for that, rho is equal to limit y tends to 0 y square by 2x, and now the 2 comes to the left side, so 2 rho is equal to limit y tends to 0 y square by x. And now divide the given equation by x, because we have to get, in first case we divided it with y because to get x square by 2y, but here we have to get y square by 2x, so here we are dividing it by x. So just divide it, you get it, and just take the y square by x terms little separately within the bracket, and now put it 2 row, and now x is equal to put x is equal to 0, y is equal to 0, and you used to get rho is equal to 1. That's it. But here is an important problem. So find the radius of curvature at origin for the curve. This. If you analyze this curve, so how do you find the minimum order term, whether it's y square or x square? You can't tell it by seeing it because it is in multiplication with some other coefficients. So you have to just simplify it to get terms. So just simplify it, used to get this as lowest degree term. So now if you equate this, you used to get y is equal to plus or minus x. This is not you can't say from this whether y-axis nor y-axis, neither y-axis nor x-axis is a tangent at origin for this curve, because it's coming as y is equal to plus or minus x. So for this we have to use the third third principle, so third method that we seen before. So we know this equation which we seen before. I have told you to remember this. So this is nothing but p is nothing but f dash of 0, q is nothing but f double dash of 0. So now we are putting it in equation 1. So y is equal to px plus q by 2 x squared in the equation 1. What is equation 1? That is nothing but the given equation. So you're putting there, and here a binomial theorem is used because it is a big series. You are going to square that series, so binomial theorem is applied, but don't worry about it. Just you take it as a plus b. So what is a plus b? So a square, and it's b square, but it comes at last, so just don't worry about it. A square plus 2ab, so 2 into a into b, you get this. So just leave it, it's enough. You get to know why it's enough in upcoming steps. So a minus x, and as it is just multiplying, you get it. Now you compare this x square and x cube coefficient to the left side x square and x cube coefficient. So that's why I told you to stop here itself, because we have x square and x cube, that's enough. So that's enough. So if you square this term, you used to get x to the power 4, which is not present in the right hand side, so that's not at all needed. This is enough. So now you compare this, you used to get ap square is equal to a. Why ap square is equal to a? Because the coefficient of x square in right side is equal to a, and the coefficient of x square in left side is equal to ab square. That's, now you have to equate it. Just equating it, we used to get p is equal to plus or minus 1. Now the coefficient of x cube, so x cube coefficients or here. So just do this. This is nothing but a coefficient of x cube in right hand side and left hand side, just equating it, and we know the value of p. So just substitute in both cases. Just you substitute, you get the this is the formula which we are going to use. So there are two cases. So in one case you used to get the radius of curvature as this, and another case is this. So since radius of curvature is a magnitude alone and it is always to be positive, so it's taken as a positive value, negative value is omitted. That's it, guys. Thank you. Bye bye.